Hello, Mr. Ryan, right?
Yeah.
Okay, so today we will look at this math problem. Okay, so given any shapes, 2D shapes like rectangle, triangle, circle, Mercedes-Benz, yeah? Any other shapes? What do you call this?
Audi logo.
Parallelogram.
Yeah, Audi logo like the Olympics.
This one, what's this?
Sort of bent square cutting.
What's this in Chinese? 日 sun. What's this?
天
Tian. Yes, it's the
Sky.
window
yeah.
Sky.
Okay.
and like Audi.
Yeah.
The Audi.
Okay.
You're an Audi one.
Audi one. Audi.
Like
Four
Olympic,
circles.
Olympic thing.
Okay. Very nice. Okay, so these are like A shapes. So we want to study to see if it's possible to use one stroke to draw all the shape, and you are not allowed to revisit the edge. We want to find out if it's possible to draw the shapes using one stroke, and you can revisit the vertex. These are the vertex, but you are not allowed to revisit the edges, same edges twice. Okay?
Good job.
Good job. Yes. Okay. So the vertex, the graph. Yeah, we talk about the graph in computer science. Graph is a collection of vertex and edges. So these are the vertex. Here we don't have vertex here, and technically we don't have edges here. But this is just one single edge. The circle is a very special shape. Okay. This one, the vertex, 1, 2, 3, 4. This 1, 4, and these 6, these 9 vertex, and lots of edges. Which of these we can finish by one stroke? One stroke. It's just like you draw a shape without leaving it, right? When you're done, right? But you cannot do this like that, right? You cannot say coming back because
Let's say you're on this delicate piece of paper, and if you go over one of the edges, then you'll go through the paper.
That's right. Yes, that's right. Okay. So which of these shapes can be done using only one stroke? One stroke.
Obviously, with the top three.
This one, this one, this one. Any more?
I'll try this one. I'll try.
Okay. Yeah, you made it. Yes. Okay. So this one as well. This one obviously. This is just similar shape. Yeah. This one.
Yeah.
Well done. Okay. Actually, this is straight line, but that's fine. How about this two?
No.
Can we?
No.
No. No.
How about this one?
Yeah, I can't do that one. Or
No.
that one.
No, that's right. Okay. So what have we learned from here? So without trying, okay, we want to study the characteristic of those shapes, these two shapes, which cannot be done using one stroke. Right? Obviously, for simple shape, you can try, right? You can try. How many possibilities for the start? There are only 9. You can try starting here. I mean, for simple shape, we can prove us. But if it's a very complicated shape, how do we tell if it can be done using one stroke? And we can start from any vertex. Okay, what are these shapes in common? This one as well. What are these shapes in common?
And
What, you're supposed to say, what do these shapes have in common?
Okay. What do these shapes have in common?
they look simple apart from the Audi one.
We study the degree of a vertex. And these are all finite graph. Finite as opposed to infinite, right? Finite graph means that it's there, it's limited, right? It's not changing. I'll give you one example of infinite graph. Let's say I mean, it keeps going.
Is that infinite
No. This is a symbol. Okay. If a graph is like that, every time, make a left 90-degree turn, you can actually draw this using turtle graphics, right? But it never ends. This is the infinite graph. We will study this problem in a finite graph. Because for an infinite graph, it doesn't make sense, right? Because the graph is infinite. We can't finish the drawing anyway, okay? But for the finite graph, we can study this problem. And a degree, put it this way, degree is the number of edges connected to a vertex. So degree for this vertex, look, the degree for this vertex is 2. The degree for this vertex is 2, okay? The degree for this vertex, 2, 2, 2. There's no vertex here, right? Or, one way to consider a circle. Does a circle have a vertex? Does a circle have a vertex?
1. No, 0.
Yeah, 0, or you can say infinity, right? They are all, lots of these vertex, right? And each vertex, the number of edges connected to it is 2. And this one, okay, let's study this one. The vertex of these is, the number of edges connected to these vertex is the degree, yeah? The degree. This is 3, right? 1, 2, 3. This is 3. This is 3. This is 1, 2, 3, okay? Here are all 2, yeah? The degree are all 2. The number of
That's
edges.
not the degree.
No, not the angle degree. The degree of the vertex. Degree of the vertex is defined as the number of edges connected to it. Here, the same, 2, 2, 2, 2. This one, 2, 2, 3, 3, 2, 2, right? This one, 2, 3, 2, 2, 4, 3. This is actually 3. 2, 3, 2. And this one, 1, 2, 3, 4. So this is 4. 1, 2, 3, 4. 4. 1, 2, 3, 4. 4. So all 4s. Okay? Okay, so if I put a number, if I label the vertex with their degree, so what do you find these in common? These in common. Not this one.
They all have
They're
the same
all-
number.
They have even numbers.
Even number, yes. If even number of what? Even. Yeah, it's something to do with the even. Okay? And then we'll talk about why is even. Look at this. 1, 2, 3, 4. Yeah, these are actually same type of graph.
They all have 2 for those 4.
Yeah, but how about this one? This one we can also do it. We have 2 3s. These are odd
There'll
numbers.
be even number of odd numbers.
Even numbers, odd numbers. That's right. Okay, so look at this. How many degrees which are odd numbers?
2.
2. Okay, so this is 2, right? We have 2 odd degrees. We have 2 odd degrees. Here we have
0.
0 degrees. Here we have 0 odd degrees. Okay? Yeah. And here we have 1, 2, 3, 4. 4 odd degrees. Here we have 4 odd degrees. Okay? So 4 odd, 0 odd, 0 odd, 0 odd, 0 odd, 0 odd, 2 odd. So what can we learn about it?
0 and 2.
Yes. So okay, so you are correct. That's right. If a graph has 0 or 2 odd degrees, then we can do it. Otherwise, we cannot do it. Okay? For the 0 odd degrees, we can start with any vertex, right? I can draw here. I can do this one shape, or I can do this. I can start from here. I can start from here. I can start from anywhere, any vertex on a 0 odd degree graph. Am I right? Look at this one. I can start here. Make sense? I can do this, right? Am I right? But for this one, for 2 odd, we can only start from the odd degree. We can either start from here or here. One is the start, the other is the finish. Or this one is the start, the other one is finish, right? Look, I start from here. Yeah, or I start from here. Right? Make sense? And all others, no, right? Okay, do you get it? So the requirement is that 0 odd, or 2 odd, right? Odd degrees. Why? Okay, so the next question is why? if we want to draw in one stroke, so for the vertex in the middle, right? We start from somewhere, some vertex. We finish on the some vertex. For any vertex in the middle, there will be one edge entering and the other edge leaving. So it has to be even. Make sense? If we enter a vertex here, we must leave it. We must be able to leave it using other edge. If not, then we are trapped in this vertex. Am I right? Unless it's a start or finish. If it's a start or finish, at the start, I don't have to come back. Am I right? At the finish, I don't need to leave again. Am I right? If we have only two odd, then one of them must be start, the other one must be the finish. If we don't have two odd, if all the degrees are even, then we can start with any vertex and then come back to it. Am I right?
Yeah.
Okay. The sum of all the degrees are even number. Am I right?
Yeah.
Look, what's the sum of all the degrees?
4
8.
8, yeah.
This is 6. What's the sum of all degrees?
12.
12. 8. This is the 14, right?
Oh,
14.
oh yeah.
What's this?
24.
So it's all even number. Why? The number of degrees, the sum of all the degree, right? Sum of all the degree vertex I, V belongs to V, is even number. This is pretty straightforward. Why? Because look, an edge contributes to two vertex, right? You see, this edge, two vertex. The degree, I have one edge. What's its contribution to the sum of the degree? 2, right? It connects to two vertex, am I right? So the sum of all the degree is actually equals to 2 times of number of edges. Yeah, 2 times the number of edges. Then this is the even number, am I right? Yeah, this is the even number. Sum V vertex belongs to all the vertex degree. If it's a directed graph, right? Directed graph. In degree is the number of edges coming to it. Out degree is the number of edges leaving it. Okay? But here the degree is the sum of the both in degree and out degree. And we have this. We're going to talk about this in the next lesson. The number of odd degree vertex is even. Okay, look, there are 0, 2. 0, 2, 4, 6. It cannot be 1. Can you draw a graph with only one odd degree vertex? You cannot. You can try, but you cannot. Look. Right? This is a simple graph. The number of odd degree, this is 1, 1. 1 plus 1, 2. Right? Yeah? Okay, I do another one. How many odd degrees? This is 1. This is 3. 1 and 1. And 3 plus 3 equals 6. Okay, so you cannot find a graph with only one odd degree. What's
I'm
that?
trying to make a shape. Wing.
Too complicated.
Okay, this is 3.
Mm-hmm.
This is 2.
And you forgot this. When you draw this, here there's 1 here.
Oh.
Yeah? Am I right? Yeah? The number of odd degree vertex is even. Okay? We're going to prove this in the next lesson. Okay? A Euler path is that a one stroke. We can draw the shape using one stroke. Then that's a Euler path. If we are be able to start from one vertex and finish it in the same vertex, then we call it Euler cycle or Euler circuit. If every vertex in a graph has even number of degrees, then we have a Euler cycle because we can start from any position and come back to it. If we have two odd, right? If we have two vertices which are odd degree, then we have a Euler path, right? We must start from one and finish it in another, okay? If a graph has a Euler cycle, then there must be a Euler path, right? But not the vice versa, am I right? Make sense?
Yeah.
Okay? Do we have a Euler path
Do
here?
I have this big row of this so we can do it with one stroke?
Yeah.
4, 4, 2, 3, 2, 2, 3, 2, 2,
Okay, how many are odds?
2.
Okay, so can we? Yes, there's a Euler path. And which way we need to start?
I would do 2 odd numbers.
Yeah, so we can start here or we can start here, right? So let's try to draw. Okay? Yeah.
You skipped this one.
No, I didn't.
Yeah, you did. You were like this. Bum, 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 bum.
Okay, and the last one. Yeah? Okay.
Yeah.
You see the Euler circuit? You see the Euler circuit? No, because we cannot start with any. There are 2 odd degree vertex. For a Euler circuit or Euler cycle, it requires that every vertex has even number of degree. Every vertex has even degrees. Okay, this is the requirement for Euler cycle. Another graph.
Yeah, you just done like this.
Okay. Yeah. 2, 4, 4, 2, 2. Each corner is 2, and the middle intersection is 4. Each vertex is has even degree. Each vertex has even degree, so it's a Euler cycle. This graph has 2 odd degree vertex, so we can find the Euler path. Okay, and in order to find the Euler path, we need the graph to have 0 or 2 odd degree vertex. Okay, so what have you learned today?
About trying to find a shape.
Describe one sentence. What have we learned today?
We learned how to check if you could draw a shape with one stroke.
Okay, and the requirement is
Euler cycle.
the requirement. Yes, and how do we check? How do we determine if a graph can
We
be
go
done?
to edge thingy,
Yeah, we count the.
every corner thing, and then you count how much lines it connects to,
Yeah, how many edges connected to it, right? Eric?
and then if
Mm-hmm.
they're even, you can do it. If they're all odd, you can't.
No, 0 odd or 2 odd, then we can. If it's 0 odd, then it's a Euler cycle. We can start
And
at
I'm
any
talking
position.
about the rest.
Uh-huh.
If they're all of the ones are odd, then it depends on how much. Then it is a failure.
Okay, Eric?
Yeah.
Oh, that's simple. That's brief, that's very concise. That contains lots of information. Okay, any more?
No.
Okay, say something.
Can I draw something?
Yeah, sure.
Okay. I just draw a random shape.
Okay.
Why not get this
Yeah.
and give it some that? Someone's at the door.
Yeah, I know, it's just the.
So this 2, 2, 4, 4.
4, eh?
4.
Yeah.
2. 3. 3. 2. 2.
Okay, so you must start from here or here, right?
Yeah.
Yeah. Okay, so that's the thing. Start from this.
Yeah. But you overlap.
That's okay. We can overlap the vertex, but not the edges. Each edge is visited exactly once. Yeah. Okay, that's it for today. Bye bye.
Bye.
Bye.